Chapter 9, Set A. In June 2005, which city was warmer, Boston or New York, or were they about the same? So we're looking, where do we find that? So on 142, we're going to the top graph. How are you going to decide? Now, that's not the R value. The R value just tells you the association between the two variables. Does it matter which graph we look at, the Fahrenheit or the Celsius? No, it doesn't matter. So let me take a picture of this. Let's draw our football. Do we have a very good football? Not really. And it says our correlation coefficient is 0.5, which is pretty weakly associated. Let me start doing this. How is that going to help? I'm connecting. Yeah, I'm just looking at the distances. And we would probably say that our regression line is right there. Would you agree? Maybe a little bit to the right. Right there. That would be our regression line. Okay, well, looking at the regression line, if New York is 85 degrees, then Boston would be about 85 degrees. So that's pretty close. So if New York were 100 degrees, Boston would be 110. Okay. If New York were 70 degrees, Boston would be about 62. So if New York is 80, Boston is 80. Now, if we got rid of everything except that line, so we think the line is about right here. Which one? Oh, that's a better line. Let's look at the 100 again. So the 100 would be about 98, and the 65 would be about 68. They're really close. So I would say about the same. What did the book say? Same? Yeah. That one's so close it's hard to tell the difference. B. In the left-hand panel of figure 2, all the dots are above the 45-degree line. Why? So we're graphing the maximum and the minimum. How come everything is above the 45-degree line? There were no numbers less than 45 degrees. That would be the minimum value. Okay. 2. A small data set is shown below. R is 0.76. Is that a high correlation? Yeah, 0.76 is pretty high. It would be somewhat representative if you were estimating. If you switch the two columns, does this change R? No. So if we take our football and we shift it to the right, does R change? So that's adding numbers to the x's. Okay, what if we shift it up? Does that change R? Nope. Wow, I killed the smartboard. That? Huh. That was weird. What if I move both of them? Does that change R? Okay, what if I multiply everything by a number and make my football bigger? Does that change R? As long as I multiply both of them. What if you just multiply one side? Does that change R? That's going to change R. Okay, so in 2, no. Switching the X and Y, not going to change R. Number 3, as in exercise 2, but you add 3 to each value instead of interchanging columns. No, doesn't change R. Exercise 3, you double each value. Does that change R? No. Exercise 5, you interchange the last 2 columns. In exercise 2, you... What did it mean you interchange the last... Oh, the last 2 values. Sorry, I said columns. Yeah, so we turned 4, 5, and 5, 6 into 4, 6, and 5, 5. Is that going to change R? Yeah, because we've moved 2 points and left all the others the same. Number 6, suppose the correlation between X and Y is 0.73. Does the scatter diagram slope up or down? Up. Is it a steep slope or a shallow slope? We don't know. R does not tell you how steep the slope is. It just tells you positive or negative and then how close the points are to the line. Okay. B, if you multiply all of the values of Y by -1, would the scatter diagram slope up or down? So we're going to let me get rid of this. So we take all of our points, and it slopes up, and then this point, 1, 2, turns into 1, -2. So it's going to end up looking like this. Man, my smartboard is all sorts of weird. Yeah. That's new. That's never happened before. C, if you multiply all of the values of Y by -1, what happens to the correlation? It's the same number, but it would be -0.76. Okay. 7, 2 different investigators are working on a growth study. The first measures the height of 100 children in inches. The second prefers the metric system and changes the results to centimeters by multiplying by the conversion factor 2.54. A scatter diagram is plotted showing for each child its height in inches on the horizontal axis and its height in centimeters on the vertical axis. If no mistakes are made in the conversion, what is the correlation? What's the correlation between measurement in inches and measurement in centimeters? They're going to, it's going to end up, so this is in inches. So let's say I have 10 inches. When I convert that to centimeters, what's it going to be? 25.4. So it's 1 inch is equal to 2.54 centimeters. So this would be 25.4 centimeters. What about 20 inches? It's going to be twice this big. 50.8. And then halfway in between is going to be halfway in between. It's going to be a straight line where every point is exactly on the line. So the correlation coefficient would be 1. Now that scatter diagram doesn't do anything for us, right? We knew that. We didn't need to graph it to realize that. What happens to R if mistakes are made in the arithmetic? The more mistakes that are made, the smaller R is going to be. What happens to R if the second investigator goes out and measures the same children using metric equipment? Should it matter? So one person measures the kids with a yardstick that has inches, and one person measures the kids with a meter stick, which has centimeters, and then we graph them. It should be the same, but it probably isn't going to be. How come? The person with the inch measuring is probably going to stop at the nearest inch or half inch, and then the person with the meter stick might do millimeters, centimeter, a 1 decimal. But are those lengths going to measure up perfectly? It'll be really, really close, but they're probably not going to be exactly the same. Is that what the book said? Yeah, it's going to be just slightly less than 1, because in this case, we are using the 10 to convert. So if I measure 10 inches and all you have is a yardstick, what are you going to come up with? Or sorry, I measure 10 inches and you have a meter stick. You're probably going to measure 25.5, right? So instead of the points being exactly on the line, they'll probably just be super close to it. And in fact, this happened once in a really, really expensive mistake. A couple countries got together and sent some kind of rocket to Mars, and they sent the rocket to Mars, and it takes a couple hours for the transmissions to come from Mars back to us, and I don't remember the name of it, but anyway, it was getting close to Mars, and they're monitoring it, and then the transmission stopped, and the rocket just smashed into the planet. It didn't slow down like it was supposed to. I'm not sure if it had rockets or parachutes or whatever it was, but it just didn't work. It crash landed. And it turned out that some people were doing their mathematics in inches and some were doing them using the metric system. Well, there was just enough of a mistake and a misinterpretation that something fouled up, and we lost whatever it was we sent there. It just crashed into the planet. Yeah. Yeah, it didn't work. Wouldn't it be nice if we could just go to the metric system? Oh, it'd be so nice. Okay. 8. In figure 1 on 120, the correlation is 0.5. Suppose we plot on the horizontal axis the height of the paternal grandfather, not the father. The height of the son is still plotted on the vertical axis. Would the correlation be more or less than 0.5? Why less? So, tall parents usually have slightly shorter kids, and really short parents usually have slightly taller parents. So if you have that happen so if the grandfather's really tall, the son is probably less tall, and then the grandchild could be a little bit taller or maybe shorter. So is the correlation going to go up or down? Probably down. 2 weathermen compute the correlation between daily maximum temperature for Washington and Boston. One does it for June, the other does it for the whole year. Who gets the bigger correlation? So 2 weathermen compute the correlation between daily maximum temperatures for Washington and Boston. One does it for June, the other does it for the whole year. Who gets the bigger correlation? Daily maximum temperatures. So, yes. Okay. Here is January, July, and December. What would we expect the whole year to look like? A big U. It's probably more like a sine wave, right? The temperature goes like this throughout the year, right? But we're just going to look at one year. So the points are probably like this. and if we just look at June and we graph it, it's going to look like that. Which one has a higher correlation? Definitely June. Does January to December have much of a correlation? Yes, but it's not linear. Okay? The R value only tells you linear correlation. And if we were to draw a line, it would look like this. Is that line very predictive? No. Now you could do a sine wave correlation, but we don't do that in this class. Yeah, June is definitely going to have a higher correlation. But the correlation in the other one is totally worthless. Okay, 10. 6 data sets are shown below. In 1, the correlation is 0.85. In 2, the correlation is 0.78. Find the correlation of the two for the remaining data sets. No arithmetic is necessary. What do you notice about set 3? So 3 has just switched the x and the y. So the correlation is going to be the same. 4 is just... How does 4 compare to 1 or 2? 4 is just like 2, only the x's have been added 1. So that would be shifting the football to the right. Does that change the correlation? Nope, so 4 and 2 have the same. What about 5? Uh, 5 is like 1, isn't it? 5 is like 1 that has been, or sorry, 2 is double 1. So if we multiply all the x's by 2, does that change the correlation? No. And 6? It's triple, the y value is triple 2, and then the x values have been subtracted by 1. So that's going to be the same as 2. All right. We're done.